Okay, I'm going to do this. I'm hearing way too many. I don't know how to do this. Okay, so let's just run through this. I think we've spent about 10 minutes to figure out the order. I mean, we know it's going to be done quickly, so we know the correct order is this. So let's just write this on the board. Those are the parentals, the largest number. That means one of the parental chromosomes is S plus, T plus, and P. And I think the other one was S, T, P plus. Is that correct? Yes. Okay, so now what are the recombinants that you should write if it was a combination event between the S and T? We had no problem doing it here. Everyone said, oh yeah, no problem. Let's do it now. It would be S plus, T, P plus. This is between S and T, and S, T plus, and P. Is that correct? Plus the double recombinants. Because the double recombinant is indeed S plus, then the T, and then the P. It's true that it was a double recombinant, but it still falls in the category of a crossover between the S and T. And then the other one, which was S, T plus P. So then we just put in those numbers. And what are those numbers? S, T plus P. 195. And that's 400, I believe. And I hope there's 1,000 progeny. So it's 400 over 1,000, 40 map units. Okay? Anyone not see that? Yes, question. I can't hear you at all. So it should be S plus T, P. And S, T plus, P plus, yep. Okay. Any other questions? All right. So everyone can do that? Good. It's going to be in the lab exam. Not that question, but application. Question in the back. Okay. If people could be a little quiet, I can't hear really. Yes? Okay, so the question is, how do I know? I'm not going to paraphrase your question because I can't even barely hear you. So I think your statement is, how did I know which ones to pick and the numbers? Is that fair paraphrasing? Okay, so let me go over this again. Since this is a parental chromosome and this is a parental chromosome, when we have them like this and we duplicate them like this, and we get a crossover between the S and T, it would be S plus, T, P plus. Do you want me to color code it again? I can color code it if that helps. I have no problem doing that. Green, white. So the green will come up like this, S, T, P plus, and the white will come down like this, S plus, T plus, P. So it would be S, T, P plus, that one, and then the S, T plus, P, that one. Is that clear? And then the double recombinant was this and this. Okay, I hope you can see how this is universally applicable. Okay, let's move on. Okay, questions? So the question is, does the difference between T and P play any role in the double recombinants? It does affect the number of double recombinants because we can use this data here. If this number was higher than the 0.1, what would happen to this number? It'd be higher. Because this is the probability of those two numbers. So yes, the distance between the here and here affects the number of double recombinants because it affects the overall distance. Okay? Any other questions? Yes, back. So the question is, are these probabilities? These are actual number of offspring. Okay. These were percentages, which is the same as a probability. So 0.2 is the total number. So you'd find 20% of the offspring having this phenotype or genotype. You and I can talk about it after class, okay? No, that's fine. We can talk after class. I don't want to take lots of time to do that right now, okay? I'd like to move on, but just come down after class, okay? Okay, so genetics problems. Determine the number of traits, the alleles of each, probability event, probability independent events. So I'd like to do this problem right now. I'll give you 5 minutes. I'm going to regret erasing that. Okay, one more minute. What's your question? So when you do the search, you'll get a list of responses. The first hit's the top one. Because it gives a list. So if you count it down to 1, 2, 3, 4, it's the first one. Does that make sense? Okay. No? Yes? Okay, let's quick do this. Let's look at the traits separately from one another. Okay, so analyze the traits separately from one another. So what we see here is we have striped abdomen and normal abdomen. So let's just do this. We have a male striped abdomen, normal legs, female striped abdomen, 8 legs. She's true breeding for 8 legs, but not for striped abdomen. So let's just quick do this. Let's look at striped versus normal. So first off, do I see a difference in males versus females for striped? No. So there's no reason for me to think it's sex-linked, because I don't see a difference between males and females. It could be sex-linked and there's no difference, but I don't know for sure, okay? And then over here, likewise for the 8 legs versus 6, I don't see a difference. So with respect to the abdomen, what's the ratio of striped to normal? What's the ratio of striped to normal? 3 to 1. What gives you a 3 to 1 ratio? Hetero with hetero. So we now know the genotype is like this, and we know striped is dominant because that's the largest number. So we now know the genotype is like this for the female, and the male is striped like this. Why am I writing in uppercase? Because the mutation is dominant. How did I know the mutation was dominant? Because the ratio is 3 to 1. Therefore, the one that's the largest number 3 must be the dominant in the heterozygote. So if you striped and striped, that makes sense because we see striped and striped. Any questions about where I came up with that? Why I chose uppercase and why it was hetero with hetero? Yeah. Because the question was, why is it hetero with hetero? The ratio is 3 to 1. The only cross that will give you a 3 to 1 ratio is heterozygous with heterozygous. I can make the cross if you'd like me to. Do you want me to put it on the board and put it on the square? Okay? Because this is 1200 and this is 400. So 1200 to 400 is 3 to 1. Okay? Anyone else need any clarification? Okay, let's do the other locus. 8 to 6. What's the ratio? 8 to 8 is 800 to 800, 1 to 1 ratio. What gives you a 1 to 1 ratio? Hetero and homo recessive. So we know that she's true breeding for 8 legs, so that's got to be the homo recessive. So we now know that since she's true breeding for 8 legs, we write lowercase, and the male is heterozygous. Okay? Now that's with them being genetically unlinked. I don't know yet. I'm going to make the predictions and see if it matches the data. It's always about the data. I either make up the data because I got to write the problem, or I get actual real data. Okay? Anyone need me to go over how? I'll go over this again. It was a 1 to 1 ratio, which is a hetero with homozygous recessive. Since this female is true breeding for 8 legs, we know they're the homozygous individual. Therefore, they're homozygous recessive, which makes 8 legs recessive. So I chose lowercase. The female is homozygous, and we said it was a hetero with homozygous recessive, so the male has to be like this. Any questions about that? I can go over it again if you want. Not seeing why it's 1 to 1. Let's do the math. So 8 legs here is 601 plus 199 is 800. 6 legs here is 599 plus 201 is 800. So the ratio is 800, 800, 1 to 1. Yes, question? Okay, we're doing that next. So great segue. The question is, how do we determine if it's unlinked? I wrote the notation right now as though it's unlinked, but I'm not sure because I haven't done the actual check. Okay, so how do I know that the 8 legs is recessive? Because do you understand that it was a homo recessive with heterozygous? Okay, and it says this is true breeding for 8 legs, so it's true breeding homozygous or heterozygous? Homozygous, so only one of the individuals can be homozygous recessive, so it must be this one, so I know 8 legs is recessive. Okay, now let's quick do the predictions. If these are unlinked, we said 3/4 should be striped abdomen, and 1/4 should be normal. And if these traits assort independently, then 1/2 should be 8 legs, and 1/2 should be 6 legs. So my prediction is 3/8 should be like this, striped, and 8 legs. 3/8 striped, and 6. Again, same application, 1/2 8 legs, and 1/2 6 legs. So it'd be 1/8 striped, 1/8 normal, 8 legs, and 1/8 normal, and 6 legs. Because we are checking to see if they're unlinked or not. We treated them as separate loci. We came up with the 3 to 1 ratio, the 1 to 1 ratio. We did all that. So if these are indeed unlinked, I would expect 3/8 of them to be striped and 8. And is that correct? Yeah, pretty much. 600 is 3/8. 3/8, 1/8, 1/8. So are they unlinked or linked? Unlinked. So when I wrote it this way, that was correct. It matches the data. They are genetically unlinked. If it didn't match that 3/8, they would be linked. Okay? And notice, I'd have to look at this one because it could have been the wild types were on the same one. So let's just extend this because we only have 8 minutes. So let's just extend this way. I actually did this last time, so we'll do it again. So this is case number 1, but I would like you to write the genotype if these 2 traits were genetically linked. And just write it for the male. Just write the possible genotype for the male if it was linked. And we know that male is heterozygous for the 2 loci. Autosomal, not on the sex chromosome. Okay? So write that notation, what you can come up with. You should have 2 different possibilities. Yes. And I'm going to call on volunteers. Should I call on volunteers or should I do it? Volunteers or myself? Just do it, okay. I think you meant just pick a volunteer. Is that what you meant? No. Okay, so one possibility is that it's like this, where the wild type alleles are on the same chromosome, or it could be like this. In words, this individual is heterozygous for both traits, and in words, this individual is heterozygous for both traits, right? So let's make predictions about the gametes that would be made. So let's do case number 2. Right? The 4 types of gametes this individual could make, put the letter P by the ones that are parentals, and the letter R by the one that are recombinants. Okay? So there's 4 types, right? So raise your hand if you cannot do this. Raise your hand if you cannot do this. Okay, I'll close my eyes. Raise your hand. Somebody tell me the number of hands you see up. My eyes are closed. I'm at 4 hands. 4 hands out of 300 is not bad. So let's quick do this. Maybe my eyes. Okay, you didn't trust me. Okay, now raise your hand. How many numbers now? 50. I have eyes in the back of my head though. It wasn't 50, was it? It was. Okay. So let's do this. Parental, SAEL plus. What's the other parental? SAEL. What's the recombinant then? SA plus EL, and the other recombinant SA EL plus. Anyone not see that? I can go over it again if necessary. I hope you see trends, patterns, reemerging time after time after time, and I hope you see that it's reflective of meiosis and how this notation system is so useful. Okay, so let's quick do this. Now let's do the 4 types of gametes number 3 can make. Okay, I'm done. It's already on the board. The 4 types are parental and red. That would be that one, this one, that one, and that one. So they make the same types of gametes, but are they in the same probability? No. So if I had data and I find that my largest number of offspring are wild type, mutant, then I know it was like case number 2. And if I find most of them being wild type elongated or mutant normal, would be case number 3. You have a problem in your worksheet that will require you to make this very distinction. So remember, it isn't always true that the wild types are coupled, although for teaching purposes, I oftentimes do that. So let's do one more problem. Okay? We are going to jump to this one. Okay? Now that one's too easy. Okay, do question 24 here. Now let's do 20. Yeah, let's do 24 and 25. Okay, let's go ahead and I'm going to do, let's quick do this now. We have about 2 minutes, so let's quick run through this. Okay, first off, we have a homozygous recessive with a heterozygote. How many will have the genotype homozygous recessive? 1/2. It's a hetero with homozygous recessive. 1/2 will have the genotype. Let's quick do the D. We got a heterozygote with a heterozygote. How many will have the homozygous? 1/4. 1/4, that's a genotype, not phenotype. It wasn't phenotype big D, or sorry, D plus. It was genotype D plus or D plus. So 1/4 will have that. Does anyone need to make that Punnett square? No? Excellent. Now for this, how many have the B plus, C plus, and the BC? It's unfortunate because I can't write uppercase C very well on the board. But let's quick do this. We'll see how fast it is. The map distance was 10 map units apart. So that means my parentals are, this together is 0.1. That makes this 0.05, 0.05, makes this 0.45, 0.55. These always have to equal 100% or 1. And likewise in this, the map distance is the same, 0.45, 0.45, 0.05, and 0.05. And if you notice in this case, the wild types are indeed coupled, but in this case they're not. So we want, what genotype? We want this. So let's look at this. Is this a possibility? Let's quickly run through this. Here's our 4x4. What I do oftentimes is I quickly eliminate boxes. Remember, within a Punnett square you add, and to get a probability of a box within here, you multiply the 2 probabilities together. So within here you multiply, within the Punnett square you add. So will this meet our criteria? No. Nor will it ever, because the BC plus isn't a possible one. So none of these will ever meet. That's a no, no, no. Because we're never seeing that chromosome in here. Likewise, the B plus C here, this way is a no, no, no. This BC is a possibility, but what does the other chromosome have to be? The B plus C plus, which is this one way over here, so that's a yes. And what's probably that box? It is 0.05 times 0.45. Anyone not see that? Raise your hand if you don't see it. Do you see how I'm quickly eliminating boxes? And then over here, let's see if we have this. We got the B plus, C plus there. We did that. So we got to do the B, C here, and the B plus, C plus here. And then this is another green. Yes. Are those the only 2 yeses? I think so, right? What's probably this box? Again, it's 0.05 times 0.45. So I have to add this to this, because within Punnett squares we add. Is that clear? So then that's the probability, which it's 2 times that. So that would give me whatever that part is. So it should be one of these in here somewhere. Okay? So enjoy lab. Start doing some problems.